All right, so welcome to Math 383 Complex Analysis. This is lecture 25, and we're now going to get an update on the great running tally of whose name has been mentioned most.
61 Cauchy.
61 Cauchy. And how many Riemann?
61.
Wow. Okay, so that is damn close. Okay. And so for today, we're going to be talking about Fourier series. So if he were being added to the list, he would be getting a lot of credit over the next few lectures.
Yeah.
Oh, he's on the list now?
Yeah.
Excellent. All right. And so we'll talk a little bit about some concepts you've seen, hopefully in linear algebra, basis functions and relations, inner products, and then Fourier series and transforms. And we'll talk about convergence. So a lot of times it's not a big deal to just write something down, but can you actually show that it converges to what you want it to? That's going to be the difficulty. The general item or piece of advice is that the smoother the function, the better the results. So in homage to whatnot, I will, oh, we already have the Java update option. Okay. I will just put in a little plug for the local economy with the smoothie spot. But as a general rule, the more times your function is differentiable, the better results you get about convergence. And that you can typically convert results about differentiability and your k-fold differentiability to how rapidly certain things converge. All right. So we had talked about Riemann's zeta function. We talked about how we could complete it. And there are many different paths. If you only want to complete it to the real part of s is greater than 0, was not that big of a deal. If you want to get to the entire complex plane with a pole at s equals 1, the proof we used involved the theta function. And the theta function is closely related to the omega function. Your theta is going from negative infinity to infinity. Okay, well, when n equals 0, that's just 1. And so it's essentially just the the negatives and the positives just reinforced. And we have this beautiful result relating omega at 1 over x to omega of x. And when you look at this, equivalently, it's a result about theta relating theta at x, 1 over x to theta of x. Where do these results come from? Well, when you look at these sums only involve real variables. There is no imaginary numbers in these at all. But there is a great quote, and I'm going to butcher it a little bit. Oftentimes, the fastest path between two truths about real numbers is through the complex plane. So just because we're not using complex numbers at the start or the end does not mean that it is a bad idea to take a detour. Why? Why do we want to take a detour into complex analysis? We have all those theorems. And what's great about these theorems? They're powerful. They're amazing, right? We can use words like this. In a math paper, it has to be dry. But in the classroom, we can say, my God, these results are remarkable. When you look at the accumulation theorem, this is remarkable what you get from that. And so by converting to the complex plane, we all of a sudden have these tools available. Now, they don't apply to all functions, but they do apply in many settings. And so we want to try to understand, where does this miracle come from? Where does this summing of n converting a sum of the function at 1 over x to the function at x? Okay. So just to give us a little picture, a lot of this was developed from trying to understand physics. In fact, a tremendous amount of mathematics is being developed to try to understand physics. String theory is a great example nowadays, or the asymmetric theory that they have in Big Bang. Hopefully this will lead to some good, interesting mathematics. This was trying to understand the flow of heat in various physical systems. And this led to the introduction of Fourier series, and it led to being able to solve a variety of differential equations. And then the question, of course, is when you write something down, can you actually prove that it converges? Can you prove that you can justify all of the operations? Physicists are often very good at having an intuition of when can you write something down that can be justified later by the mathematicians. And so if you restrict yourself to certain spaces, this can all be justified and made to work. All right, so now it is that wonderful time of the class where we get to see who remembers their linear algebra. All right, so I know it's been a while for several people. So we talk about the dot product or the inner product. And so we'll say v dot w, and we often denote it with angular brackets. Does this look familiar to anybody? Anybody here seen the bracket notation? We can quickly see who's taking the physics class. Okay, so there's lots of different ways of writing this. And we define it, at least in a finite dimensional Euclidean space like Rn, or Cn as the sum of Vi, Wi, where obviously V is just V1 through Vn and W is W1 through Wn. So the biggest thing to note is, why are we taking the complex conjugate? Yes.
We want something done with itself.
Yeah, we want something dotted with itself to be real, and in fact, more than that, to be non-zero, and in fact, more than that, to be positive, unless, of course, it's the zero vector. Yeah.
Dot product the output of real numbers regardless. Like it's the function from input.
I don't think the dot product has to output a real number. The dot product of something with itself, its length, has to be a non-negative number. But just the general dot product of two objects does not have to be, because over here, if I just take V to be, and again, I am doing what you should never do, I'm using I as an index of summation. But if you just take V1 to be I and W1 to be 1, its output would just be I. So it's okay if the dot product is imaginary. It's okay if the dot product is complex. It's just the dot product of a vector with itself should be non-negative. So without complex conjugation, if we did the vector 1i dotted with 1i, that would be 1 squared plus I squared, which would be 0. And you would have the length of the vector 1i would be 0, and we don't want that. So this is a natural definition. How many people have seen the definition of the dot product of the inner product on the space of continuous functions? How many have not seen the dot product on spaces of continuous functions? Okay, interesting. Okay, so we're going to define f dot g to be the integral, let's say, from 0 to 1 of f of x, g of x bar dx. And I'm working on just the interval 0, 1. If I wanted to work on the interval all of r, I would just integrate from minus infinity to infinity. Why is this a natural definition? So let's do some motivation. Hopefully you've seen this before. Let's associate f to the vector f of 0, f of 1 over n, dot, 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 f of n minus 1 over n, f of 1. And g to be the vector, g of 0, g of 1 over n, dot, 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 g of n minus 1 over n, g of 1. Do you agree that as n gets very, very large, this n-dimensional vector is a pretty good approximation for our functions f and g, at least if they're continuous? And so let's define this to be maybe fn, and define this to be gn as just some vectors. And then if I look at fn dotted with gn, that would just be the sum. K goes from 0 to n. And again, maybe I should only go up to n minus 1. Doesn't really make much of a difference. I'll go up to n minus 1 of fn of k over n, gn of k over n bar.
Why are you going for n?
Just so that I have n items, not n plus 1 items. Doesn't really make much of a difference. So this is a nice object, but if I take the limit as n goes to infinity, the right-hand side almost surely is going to blow up. What should I do to make the right-hand side nice? Yeah, put in a 1 over n. And now, if I take the limit as n goes to infinity, this will go to the integral from 0 to 1 of f of x, g of x bar dx. How many people have seen a motivation like this before? Or at least some people have seen this motivation. So this is a good way to justify why we are using this as our definition. It's a nice way to just extend what you've seen in the finite dimensional setting. And by putting in this factor of 1 over n, it's going to have nice convergence properties. At least if the function f is continuous and g is continuous. Okay, so now there's a bunch of standard things that you can prove. I'm not going to do this. You should be able to do this. You should be able to prove that the inner product of f with itself is non-negative and equals 0 if and only if f is identically 0. But you might think, wait, well, that's not true. If I have a function that's 0 everywhere but 1 at 1, well, that's where we look at the conditions and we see that I'm assuming f, g, and h are continuous functions. How many of you have taken measure theory? All right, so if you've taken measure theory, what would you replace is identically 0 with? Yeah, you're going to replace it with almost everywhere. And so if we work with continuous functions, we don't have to worry about small sets of exceptions. So we're not going to really worry about that. The next one is that if we flip the order of f and g, it's the same as taking the complex conjugate. And what we're crucially using here is the complex conjugate of a product is the product of the complex conjugates. And of course, the complex conjugate of the complex conjugate is itself. It just returns back to where you started. And then the last one is a kind of linearity property. If we have AF plus BG dotted with H, it's AF dotted with H plus BG dotted with H. So it's linear in the first component. All right. And then the next is the definition of the word orthogonal. So we say two functions are orthogonal or perpendicular if their inner product is 0. Orthogonal just sounds more prestigious and snooty, than just saying perpendicular. For us, we are constantly going to use the functions en of x is going to be e to the 2 pi I n x. And then the dot product of two functions em of x and en of x is going to be 1 if m equals n and 0 otherwise. Yes.
I know that the perpendicular intuition comes from vectors that are actually perpendicular, but what does it mean anything besides their inner product is 0? Like if they're
The way you should really be thinking about it is they represent perpendicular directions. And so we're going to try to expand functions in terms of a basis set of functions. And just like in normal space, it's really convenient if you have a coordinate system of mutually perpendicular directions. We want to have the same thing here. So what does it mean for functions to be perpendicular? This is the generalization. And we should hopefully have a similar type of expansion. And so here, we basically take x lives in the interval 0, 1, or minus 1/2, 1/2. As long as we take an interval of length 1, doesn't really matter. And then we have en of x, their dot product is equal to 1 if m equals n and 0 otherwise. Where have we seen this result before? So where have we seen this result that em dotted with en is 0 unless m equals n, in which case it's 1?
You use them like counting zeros?
Not quite counting zeros, but it's close.
is this the integral along the circle is 0?
Yeah. Yeah, this is just integrating the integral over a closed circle of z to the k dz equals 2 pi I if k equals -1 and 0 otherwise. Because what we're really doing here is we're integrating along the circle of radius 1. And remember, dz, if we have z equals e to the I theta, dz is going to be I e to the I theta d theta, so it's I z d theta. And so if you just go through and just chase all the constants, I'm doing e to the I theta, maybe we should do e to the 2 pi I theta. When I plug this in, when I have a d theta, the d theta is really like a dz over z. And for there to be a contribution, then I can't have anything in front of that dz over z. And so if m equals n, they perfectly cancel. Because remember, we take the complex conjugate. This is going to just be the integral from, say, -1/2 to 1/2 of e to the 2 pi I n, so I guess m minus n of x dx. Because I take the complex conjugate of the second part. So if m equals n, we're clearly just integrating the function 1 over an interval of length 1, so that's clearly going to be 1. If n does not equal m, then we have cosine and sine with an integer number of periods. And if you just do the integration directly, you'll get that it's equal to 0. So there's a lot of ways to see this, but really, this is just the fundamental integrals we've been doing from the very beginning of complex analysis. The integral of z to the n, about a circle of radius 1 centered at the origin. The only time it's not 0 is if n equals -1. So we're still fundamentally using that relationship. So we have -1, as I said, oops. Because if z is e to the I theta, dz is e to the I theta d theta. And so instead of using theta, I guess I'm using x, doesn't really matter. So d theta is dz over z. So when I'm trying to convert this, if m equals n, this is going to look like just dz over z. Okay, so the next is just some standard notation that hopefully you've seen before, at least the first one. A function is periodic. With period a, if every time I increase by a, I come back to where I started. And what are great examples of periodic functions? Sine and cosine, anything else? Tangent, anything else? Complex exponentials, e to the 2 pi I and x. Well, not surprisingly, because e to the 2 pi I and x is cosine 2 pi nx plus I sine 2 pi nx. There's a relationship between the trig functions and the complex exponentials. We can define sines and cosines in terms of the complex exponentials. This is why, of course, the angle addition formulas for sine and cosine look a little similar to those for the exponential function, because they're all related. So we define the nth Fourier coefficient of a function to just be the projection of our function in the direction of en. So it's basically f of x e to the -2 pi I and x dx. So instead of integrating from 0 to 1, if it's periodic, I could, of course, integrate from -1/2 to 1/2. I'd choose any interval of length 1. And so the Fourier coefficients, sometimes we write them as an, sometimes we write them as f hat of n. You always want to think of good notation. The hat is to remind you that it's coming from your function f. It's related to something you've seen. And the hope is that if I know all of the Fourier coefficients, I know the function. And the hope is that maybe I can represent my function as a sum of amounts in the different directions, or these different projections. This is the same idea of if I give you a real symmetric n by n matrix. As soon as I tell you real symmetric n by n matrix, what do you know? And don't say it's a real symmetric matrix that's n by n. Real eigenvalues. And it's diagonalizable. So you can represent any vector as a linear combination of eigenvectors, which means if you want to apply powers of the matrix, it's really easy, because applying the matrix, m times is the same as applying it m times to each eigenvector. And you can understand the behavior of a general vector in terms of understanding the behavior of the eigenbasis. It's the same thing over here. I want to try to represent my function in terms of a combination of nicer functions. Sines, cosines, complex exponentials. All right, so we can think of the ENs as an infinite set of perpendicular directions. And again, you can either use the ENs as your directions, or you can use sines and cosines. You can go back and forth between the two. Sometimes it's more convenient to write sines and cosines, sine 2 pi x, cosine 2 pi x, sine, 4 pi x, cosine 4 pi x, and so on and so on. Or to just write things in terms of the exponentials. Really doesn't matter, you can go back and forth. Given that this is a class in complex analysis, I will almost surely use, for the most part, exponentials. Okay, and so the next exercise, which is pretty straightforward, is just chasing the definitions. Let's take the function f of x. Let's calculate its projection in the direction of the vector en, in the direction en. And then what we do is we take f of x and we subtract the projection. So the amount in the direction of en times the vector en. And then this is just saying that when you take the dot product of this with en, it's 0. Or in other words, you've subtracted everything in that direction. So again, strongly urge you to just go through, do this. This should be very similar to results you've seen in linear algebra. If I throw away the projection in the direction of the x-axis, and I look at what results, and I try to project that down onto the x-axis, I should get nothing, because I've already thrown away everything in that direction. So this is just a restatement of what it means to do projections. Okay. Any questions about the material here so far? Yes.
So we use F out of n to denote like the F Fourier. That's not really the Fourier transform, right? You're not looking at the negative infinity, or is it different?
No, we're doing Fourier coefficient.
Yeah. So, but you still use F out of n. Right?
Of course.
Okay.
We love to overload notation, right? And so it's the same thing with the absolute value. The absolute value is initially defined as just the absolute value of a real number. We extend it to the absolute value of a complex number. We even extend it to the length of a vector. When I teach 150, I actually like to do the double absolute value, 2 vertical lines on each side, to just remind ourselves that it's not a real number necessarily that's inside. We're actually working with a vector. This is why I like putting arrows on my vectors to just be able to remind myself that this is a vector that I'm working with. But yes, unfortunately, there is an overload of notation. And there is a relation between the Fourier transform and the Fourier coefficients. They're related by looking at a function that comes from collapsing certain sums. But you do have to be a little careful about the notation being used. All right, so instead of just taking the projection in one direction, we could take the projection in many directions. And let's do it symmetrically. So we'll go from minus big N to big N. And for each of these, we take the projection in that direction, and then we multiply by the vector for that direction, the En of x, and then we sum them. And this is going to be the nth partial Fourier series. And again, just for definiteness, f hat of n is just the projection of f in the direction of En. What do you think should happen if f is good as n goes to infinity? It should converge. What do you mean by converge? I'm sorry? Okay, so by equal, do you mean equal pointwise at every point? So that's the nicest type of convergence, that we have pointwise convergence, that for every point, it converges. You could have other types of convergence. You could say that if you look at the L1 norm of your function and Sn of x, that should go to 0. Or the L2 norm should go to 0. So it doesn't have to converge pointwise, it just has to converge up to some small set. So there's a lot of different types of convergence you can do. It's the same if you've taken a probability class, there's lots of different types of convergence and probability that you can have. The nicest convergence is pointwise convergence. And again, there's a bunch of exercises that you can prove. These are, for the most part, straightforward calculations. The first is, if we take f of x and we subtract the nth partial Fourier series, and then we project in any direction from minus n to n, that's 0. Well, that's essentially just an analog, a generalization of exercise 11.2.1. And you just show that it works if you keep doing it more and more. The next one is that f hat of n is at most the integral from 0 to 1 of f of x. We often write this as the L1 norm. And we put a subscript there for the L1 norm. So this is the L1 norm. How many people have seen like the L1 norm and the L2 norm in their analysis class? So in general, the LP norm would be the integral from, say, 0 to 1 of f of x to the pth power dx to the 1 over p. And a function is an LP of 0, 1 if this is a finite number. So some of the more useful ones to use are when p equals 1 or p equals 2. And there's lots of different relations. If you're in L1, are you in L2? If you're in L2, are you in L1? Does it depend on the space you're working on? So the inclusions could be very different if you're working on 0, 1 versus 0, infinity. So why do you think property 2 is true? Why do you think the Fourier coefficients are at most the L1 norm of F?
by a complex differential.
Okay,
So that might like change the direction. Like,
you're close.
Think about it as analogous or point or n. It's all along one basis vector, then that's
Okay, that's a good hope, but that's not fully rigorous.
In absolute value, that the by INX is one.
Yeah, the absolute value of e to the 2 pi ix is 1. So we use the absolute value of f hat of n is less than equal to the integral from 0 to 1 of the absolute value of f of x e to the negative 2 pi I n x dx. And that is just the integral from 0 to 1 of the absolute value of f of x dx. So we're just using the fact that the absolute value has of e to the 2 pi ix has magnitude 1. All right, the next one is Bessel's inequality. So this is a fun one to prove that the sum of f hat of n squared is at most the inner product of f with itself. This is basically the L2 norm squared. And so that's just going to be the integral from 0 to 1 of f of x squared dx. So that's a very useful result that the sum of the squares of the Fourier coefficients converge if your function is square integrable. And again, a lot of these are proved in the chapter that I've sent you. So if you do want to see details, it circles and does them a little bit later. The next is the Riemann-Lebesgue lemma. And so Riemann gets a mention. That's only count as 1, not 2. It does count as 2. Okay. That's not fair to Cauchy. All right. So he gets an extra mention here for a result in Fourier analysis. That if you have a function that's an L2, then as n goes to infinity or negative infinity, the Fourier coefficients tend to 0. And it actually holds a little bit more generally. All you need is that the function is an L1. These are great results that tell you that no matter what function you look at, so long as it's even vaguely nice, you have great convergence properties. As an aside, let me just quickly add a slide. Okay. So, L1 is functions, let's say L1 of S is functions where the integral over S, the absolute value of f is finite. L2 of S is functions where the integral over S of f squared dx is finite. What's true about this? Functions that are integrable versus functions that are square integrable on 0, 1.
Square integrable 0.
Okay, so you are saying that anything that's square integrable must be integrable on 0, 1. Okay, okay, guess. Any other guesses? So note, the integral from 0 to 1 of f of x dx is the integral from 0 to 1 of f of x times 1 dx. And you should know a good inequality to use at this point. So why am I putting in a 1? I want to have an inequality involving two functions. Cauchy-Schwarz, right? Gets someone back on the board for non-complex reasons. So that's not fair to Riemann, right? So if we take absolute values, so you should have seen Cauchy-Schwarz. This is going to be less than equal to the integral from 0 to 1 of f squared dx the 1/2, integral from 0 to 1 of 1 squared dx to the 1/2. So Cauchy-Schwarz is extremely useful in a setting like this because it's an interval of finite length. Because it's an interval of finite length, as length of S is finite, this is a good idea. Okay. And so now we see if the integral of f squared is finite, that will force the integral of f to be finite.
Not the other way around.
So so anything that's in L2 is in L1. So clearly L2 of the interval 0, 1 is contained in L1 of 0, 1, right? Because if you're square integrable, you're integrable. Can you give me a function that is in L1 but not in L2? Okay, so you're going to give me something just on the border. Okay, thank you so much. So take f of x equals x to the negative 1/2. I'm sorry? No, this will just, I'm sorry? Okay, so this will just work. Then the integral from 0 to 1 of x to the negative 1/2 dx is going to be x to the 1/2 over 1/2 at 0 and 1, which is finite. But the integral from 0 to 1 of x to the negative 1/2 squared dx equals infinity, as the integral of 1 over x is the natural log of x. So L1 of 0, 1 is not contained in L2 of 0, 1. And again, it's really valuable to just play around a little bit and try to get a sense of the inclusions. Instead of looking at 0, 1, try looking at 0 infinity. And now with 0 infinity, I have some issues because I can't just use Cauchy-Schwarz because that has no value at all. Because when I try to use that, I have the integral from 0 to infinity of 1 squared. So I get, oh, good, the L1 norm is at most infinity. Yeah, there are a lot easier ways to prove the L1 norm is at most infinity, right? So it's useless in that case. So this argument crucially uses the fact that we have a finite interval. So what this tells you is that the space of functions in the inclusions could crucially depend on some properties of the space. Is your space compact? Is your space finite? Okay. So anyways, the Riemann-Lebesgue lemma is that if we're in L1, that suffices to show that the Fourier coefficients are tending to 0.
You have the LP norm as like a 1 over c.
Yeah.
In the last slide, you had the LP norm without a 1/2. Should it be? Yep.
I didn't, well, no, I'm just saying that you're in these spaces if these integrals are finite.
Okay.
Right? It doesn't matter if I take a square root or not. If it's finite when I take a square root, or it's finite when I square it. I'm not saying that this is the L2 norm. I'm just saying you are in L2 if this integral is finite.
The thing on the top right one.
Right. It just says I need that to be finite. I'm not saying that that's the L2 norm of the function. I'm just saying if that integral is finite, then you're in L2. If I wanted the L2 norm, I would then have to take the square root. But if I'm just trying to see are you in the space, I just need to know if I take the integral of the square, is that a finite number? And so the last one is if f is differentiable k times, then if you integrate by parts, you can show that the nth Fourier coefficient decays at least as fast as 1 over n to the k. So how many people have never seen double less than? Okay, so double less than just means there is an n and a c such that for all absolute value of n greater than n, we have f hat of n is less than or equal to c over n to the k. And I guess technically here, I should have the absolute value of n because I could allow n to be a negative number. Although, no, I'll just put it like that. Yes.
Is it like big O?
Yeah, it's actually the same as big O. So if you know big O, it's just another way of writing big O notation. So it's just saying that up to some constant, we are decaying at least as fast as constant over n to the k. And this is just a really nice example of integrating by parts. What's nice, of course, is when you integrate the exponential function, you just get back to the exponential function. And then if the function is differentiable, it means it has to be continuous. And if it's continuous, you have some boundedness properties. Okay. And so you might need to assume for some of these that f is periodic. To prove, say, assume f is periodic. So again, I strongly urge you to just go through and try to do some of these calculations. So the next thing is, how many of you have ever seen an approximation to the identity? That's just what the subject is called, approximations to the identity. How many of you have seen the delta function, which is really the delta functional? Right, so in physics, they often play with this fast and loose. This is the rigorous way to define it. So I'm going to assume that you're familiar with the basics of probability, and an approximation to the identity is defined as follows. So I want a sequence of functions a1, a2, all the way up to infinity with three properties. The first is no matter what x and n I give you, an of x is greater than or equal to 0. For any n, the integral of an of x equals 1. And then the last one is given any delta, if I take the limit as n goes to infinity, the probability that I'm not within delta of 0 tends to 0. So again, what you should really be thinking about is we're working on 0, 1. If you want instead, think of it as maybe -1/2 to 1/2. Here's 0. And what I'm saying is, as if I fix a small little interval about here, as n goes to infinity, the area under an of x outside of minus delta delta goes to 0. So it's basically saying almost all of the mass of the function, almost all of the area is between minus delta and delta. But again, what we're doing is we're fixing a delta and then we're letting n go to infinity. What do the first two conditions remind you of? An of x is greater than or equal to 0, and the area under the curve is 1. Yeah, this basically tells you, an is a probability density. The last one is saying that as n goes to infinity, almost all of the mass is concentrated near the origin. So can somebody give me an example of a good probability distribution with a parameter so that I'm getting more and more mass concentrated at the origin? Okay, which Gaussian? Yeah, so one thing is let an of x be 1 over square root of 2 pi n e to the negative x squared over 2n. So this would be a Gaussian with variance n, or standard deviation square root of n. As n goes to infinity, what's going to happen in this case? This is going to become more and more spread out, right? This would be horrible. So I don't want n. I want, instead of n, I want 1 over n. So now it's a normal with mean 0 and variance 1 over n. Ah, with variance 1 over n, okay, it's getting tighter and tighter and tighter and tighter. That makes sense. I'm having a Gaussian with more and more mass concentrated in a smaller and smaller interval. So this is a really good example of a sequence of functions that's an approximation to the identity. Right? Your normal, what's nice about the normal is it's infinitely differentiable, it has rapid decay. There's only one bad thing about the normal, well, maybe two. So what are the bad things about the normal? Hard to integrate in closed form. And it has unbounded support. It goes off to infinity. What this is telling us is we got this by taking the standard normal and then just tweaking a parameter. So maybe let P of X be a probability distribution. Consider Pn of X equal P of nx times n. Is this going to be non-negative? Yeah, P was non-negative, so this is going to be non-negative. Will it integrate to 1? Yeah, just change variables, let u equal n times x. So this will still integrate to 1. What does the fact that we now have an n times x mean? Well, before, if I move in the original function P of x, if I move x over by 1 unit, that's equivalent now to in Pn of x, moving x over how much? So what motion on Pn of x corresponds to the same motion on P of x? So for P of x, if I change x by, if I start off at x equals 0, and I want to go up to 1, I move x by 1 unit. So if I start off at x equals 0 for Pn of 0, how much do I need to move to get to basically P of 1? 1 over n. So you see that you move far less now when we look at Pn of x. This is going to be an approximation to the identity. The mass is going to get more and more concentrated near the origin. So what it basically says is that if you want an approximation to the identity, just take any probability distribution and rescale. And if you rescale, it becomes an approximation to the identity. Then certain approximations to the identities will be easier to work with than others. Certain ones will lead to better examples than others. Okay, any questions about this? Okay. So as a nice exercise, if you take a continuous function and we take any sequence that's an approximation to the identity, as we integrate from -1/2 to 1/2, this is just going to go to f of 0. And essentially the way to think about this is essentially all of the mass is getting concentrated closer and closer and closer to 0. If my function f is continuous, here's the sketch. F of x equals f of 0 plus small near 0. And because f is continuous, it doesn't really matter what f is away from minus delta to delta. So write the integral from -1/2 to 1/2 of f of x, an of x, as the integral from minus delta to delta of f of x, an of x dx, plus the integral x greater than delta, f of x, an of x dx. So f is bounded. This part goes to 0. And this part goes to f of 0 times the integral from minus delta to delta of an of x dx, which is just f of 0. So you can make this rigorous, but this is essentially what's going on. All the mass is concentrated near 0, so when I integrate any nice function, I'm going to just get back f of 0. This is why we sometimes talk about functionals. Functional takes a function as input. And so here, the functional returns the value of your function at 0. And this is where the Dirac delta function comes in. Delta of f is defined to just be f of 0. And the way you interpret this rigorously is we consider a sequence of approximation, a sequence that's an approximation to the identity. And now we can just work with this very nicely. Okay. So now we can finally see why we give a DM and why this is useful for what we're doing. So we have the Dirichlet and the Fourier kernels. It should be obviously why we're denoting the first one by D. This is the Dirichlet one, and the second one is the Fourier one. And it's defined as the sum of En of x. And the second one is a weighted sum. So this is basically a weighted sum of the En of x's. If you look at Dn of x, this is just the sum of our basis vectors from minus n to n. How do you think you would prove these formulas, that the first one is this ratio of signs and the second one is that ratio of signs? What do you think the key ingredient in the proof? What do we know about these sums? What do we know about the sum of Dn of x? What kind of sum is this? Can you recognize the pattern? What kind of sum is this? It has a name. Yes. It's an exponential sum, but okay.
Yeah.
Geometric series. This follows from geometric series formula. The ratio is just e to the 2 pi I n x. And then it's just doing some algebra. But this just follows by using the geometric series formula applied to that. And then the second one is now we have to do a little bit more work. So the second one is a little bit harder, but as a nice exercise, you can prove these two. Which one do you think might be easier to work with, Dn or Fn? One of them has a beautiful property. Which one do you think has a beautiful property? What property do you think it is? Okay, convergence in what sense?
That's when big N goes to then have one of something.
It's not convergence. What is true about the second one? We haven't proven it, but what do you think might be true about the second one? This is now a function. Both of these are functions with a parameter n. I have a sequence of functions. What might be nice about the sequence of functions? If it is a approximation to the identity, right? That's what we were just doing before coming here. Now, for an approximation to the identity, we need three things. We need almost all of the masses concentrated near the origin. We need that it's non-negative and that it integrates to 1. The first one is a nightmare. It oscillates. And so the first one, the Dirichlet one, is not an approximation to the identity. This is why Fourier series is so hard to work with. However, the second one, the Fourier series, is closely related to the Fourier series. It basically gives you a weighted Fourier series. So rather than using the standard Fourier series, if you put in a few weights, convergence becomes trivial. Are you willing to put in some weights? Sure, it's not a big deal. When we count primes, we saw it's much better to count primes with a log p weight. This is one of the big themes of the class. Often you don't study what you want, you study what you can, and then you argue, well, of course, without loss of generality, this is the right thing to study. And it's much easier to study things that have weights. And then if somebody says, well, I don't want to use weights, I don't want to know how many weighted primes are less than x, I want to know how many primes are less than x. You then remove the weights. So you first study the weighted object, and then you remove the weights. And so specifically, what goes on here is we're really having what's called an integral kernel. So convolution, I think we've talked about convolution before in this class. Have we? We talked about probability distributions. If I have two probability distributions, the density of the sum is the convolution of the density. If I fix some function k, I have an integral operator. You give me a function f as input, and I do this integral, and I get a new function g as output. And depending on what function k I put in, I get different functions as output. This is an extremely valuable relation. And different choices of k will lead to different things. And I will just end today with the big result that the Fourier kernels are an approximation to the identity. The proof comes from writing things in a very clever way. The non-negativity is easy. And if you write it as follows, you can see that each thing is going to integrate to 0 except for the first term. And then the only thing that's left is proving that the mass is concentrated. So I urge you to try to figure out and put in the details of this proof. The Dirichlet ones are not an approximation to the identity. All right, so we will stop here.